Do the slides advance?
Yes, so they do.
Right, good. I don't see the audience, right? Is it the setting? I see only the panel.
Yes, so.
Oops.
Guys, we'll be beginning in a minute. Please do ask your friends to join. They don't want to miss this one. All right, so I guess we'll begin now. First off, Dr. Somak, a very warm welcome to AstraX. We're grateful that you could spare some time out of your busy schedule and address all our participants. Uh, to the participants, a small introduction about Dr. Somak. Dr. Somak Raychaudhury is the director of the Inter-University Center for Astronomy and Astrophysics, Pune. He graduated from the Presidency College, University of Calcutta, with further studies at the University of Oxford, UK. After his PhD from the University of Cambridge, he worked at the Harvard Smithsonian Center for Astrophysics, where he was also a part of the team that built the Chandra X-Ray Observatory. After teaching for over a decade at the University of Birmingham, he returned to India as the head of physics and dean of sciences at Presidency University, Kolkata, before he became the director of IUCAA. Dr. Raychaudhary is a fellow of the National Academy of Sciences, Royal Astronomical Society, and the Astronomical Society of India. His research involves a wide range of topics in cosmology and astrophysics from the ground and from space. Today, he's going to give a talk on possibly the most extreme environment in nature, and a topic that geeks like me and science fiction authors love reading, writing, and messing about. That's black holes. Uh, Dr. Chaudhary, a very warm welcome to you again. Uh, Over to you now.
Thank you very much. Thanks. I hope my sound works. Thanks, Anmol. Thanks, Jahnavi. It's wonderful. I hope your event is going well. Today, I thought I'd talk about black holes. And of course, you have another related talk coming on tomorrow to do with the LIGO, and I'll mention it a little. But this year, black holes have become even more. I mean, every year there's a reason to celebrate black holes. But this year, because of the Nobel Prize, going to black hole physics, it's become quite topical, and I'm going to touch on that. But in general, as Anmol mentioned about black holes being the kind of central theme of science fiction and movies, quite a lot of films of late have talked about black holes. I feel it generally gets a very bad press, and so one of the things that I will do, as you can see, I mean, you have all these big movies concentrating on how big and bad black holes are, as if there are things that black holes are there to suck you in and harm you, and they're out to get you. People lose sleep at night thinking about getting sucked into black holes. And I think at the end of today's lecture, I aim to set your mind at peace that there's no black hole out there trying to get you. In general, black holes are nice, friendly, benign things that are best left alone. If you go to mess with them, then they can, like any, my cat also is like that. If you mess with my cat, it can bite you. So black holes, are quite interesting things. And as long as you don't go very near them, you are safe. Now, what are black holes? And I'm sure a lot of you have read a lot about black holes. You know a lot. And so if some of this sounds a little easy or familiar, just bear with me, because what I'm going to talk about in general is how we go hunting for black holes. And in order to do that, I want to introduce the topic in a way that reflects what I'm going to do later on. So start from gravity. Everybody reads about gravitation in schools. And in general, this is what we are taught. We're taught that Isaac Newton, in a situation very similar to what we have here now, during a pandemic that was going on in England at that time, plague, the University of Cambridge shut down for 2 years, 1.5 years, more than that. So it's very similar to now, and everybody was sent home. Young Isaac was sent home from university, and during this lockdown period, he spent time at his aunt's place, which had a nice apple orchard. He sat there under apple trees thinking about things. And during that period, he invented calculus. He invented the binomial theorem. He essentially started thinking about the nature of light. And most of all, he invented the theory of gravitation. And essentially, he figured out that, and remember, he was a second-year undergraduate at that time. He figured out that the force between two objects which have mass is proportional to the masses and inversely proportional to the square of the distance. And he also figured out it's universal. And of course, he published this much later, but this is when he essentially did all this. He figured out universal in the sense that watching the apple fall from the tree, he figured out that that is the force with which the Earth is pulling the apple is the same force that pulls the moon around the Earth and the Earth around the sun and things like that. And this particular thing, and this is quite revolutionary. Right now, you don't think about such a concept as revolutionary, but traditionally people have always thought that whatever applies to the galaxies and the stars and the planets out there in the heavens is very different from what we have on Earth. And this was the beginning of science as we know it to begin with, because we started applying rules that actually apply in our laboratories to the universe, which was not really allowed before that. Started really from Galileo, came just before Einstein. Right, so from this, one has the concept of escape velocity, and that is that since the Earth is pulling us, for example, to its center, we are stuck to the Earth because of this force of gravity. Then in order to escape from the Earth, one has to travel with a minimum velocity such that the kinetic energy overcomes the potential energy due to gravity. And that's given by this very simple formula, 2gm over r square root, right? So everything has an escape velocity. If it's more massive, something that's more massive than the Earth, then the escape velocity would be much higher. If it's less massive, like the moon, you jump on the moon, you jump very high, right? And it's easier to escape from the moon than from the Earth. So it depends on that m and the r. The two are very important. It's a ratio of the two. Now, in terms of this kind of very classical gravity, and actually it's strictly this mathematics won't work because of things that I'll come to in a minute, but one can essentially understand this concept from Newton's gravity as well, of concept of black holes. It just says that, you know, we know that the speed of light is the maximum speed that anybody can attain. And if, for example, there is something that has an escape velocity that's equal to or larger than the speed of light, then nothing can escape from it. That's the idea. And if nothing can escape, then it's called a black hole. So how can you make something whose escape velocity as high as the speed of light? In order to do that, you can, for example, look at that formula. The formula has a m on top and r at the bottom. You can keep on increasing the mass of an object, and that's a very difficult thing to do in science. And in experiment, you just can't, you know, it's not like you take a cat and start feeding it carrots or whatever. You can't increase the mass that way. But what you can do is you can take something of a finite mass and then shrink it. And if you shrink it, the r goes down. And so that number, the escape velocity, starts going up. And if you take the same mass and shrink it, as you can see, if you throw something up, it goes to a certain height and then comes back again. And you need far more of a velocity in order to get to the same height and indeed to escape. This people realized soon after Newton. So Newton wrote these things down towards the end of the 17th century, beginning of, and then, as you can see, very soon after that, people started realizing that even from this kind of a concept, you can probably have a star which will be massive enough and have a radius small enough that together its escape velocity can be very high. So what will happen if light can't escape? Laplace came up with an idea in France, independently of John Mitchell, and people were already discussing this more than 200 years ago. And the concept came of dark stars. So star is so small, its escape speed turns out to be more than the speed of light. So what would this particular size be? Now, Newton's formula is not very good at calculating this, because once you start making speeds very high and it approaches the speed of light, then Newton's formula of gravitation really doesn't work, even though people had tried that. And of course, Newton essentially has no formula for controlling light, because light is massless. So the gravity in Newton's form does not act on light, right? And so you really cannot form a black hole in the strict Newtonian sense. As you will see later on, it actually requires Einstein's formulation of gravity. And from that comes this formula, which is the formula of the Schwarzschild radius, which is, it gives you the size of a black hole, which means that if you have a mass m and you shrink it, to below this particular size, radius, in spherical form, then it's going to have an escape velocity that's higher than the speed of light. For the Earth, that quantity is less than a centimeter. So you can see that it's not that easy to do. And you read a lot of news items about how when they turn on that accelerator in the LHC, the Earth is going to turn into a black hole. You know, that's not going to be easy. Yeah, so don't be alarmed. For the Sun, that quantity is about 3 kilometers. And for a long time, people thought that that's not really possible. Something like the size of the sun to turn into something which can be 3 kilometers. So we need, for the story, in order to calculate and actually quantify black holes, you need Einstein. Einstein reformulated, and in a minute I'll tell you how, reformulated Newton's theory to figure out how you can think about gravity in terms of the fact that it can attract light back. And so it's a very different way of looking at gravity. The person who, so this was in 1915, very soon after that, within a few months, Carl Schwarzschild had actually solved Einstein's equations. Einstein just put down the equations. You actually had to solve it to apply it to a particular situation, put down boundary conditions. As we know, these are differential equations, and you really have to apply it. And Schwarzschild is very interesting. He was the head of Department of Mathematics at the University of Göttingen, but he was at that time in the First World War fighting on the Russian front for the German army. And he'd taken Einstein's paper with him. Now, remember, this is the middle of the First World War. Germans are fighting against the English-speaking world, Americans and Brits, and of course, India was part of Britain at that time. And so essentially, it took a while for Einstein's theory to get out to the English-speaking world. A very interesting story of how it got to the English-speaking world through India, because the first translations of Einstein's paper was made in Calcutta by S.N. Boson and M. Saha, and it was translated for the English-speaking world. But the Germans knew about it already, and so Schwarzschild took Einstein's paper with him at the Russian front and actually solved it while the war was going on, within a few months of the paper being published. And he sent a postcard to Einstein saying, here's what I found. What I found is that if you have a sphere which has that radius that I showed you, 2gm/c squared, then you would find that no light, nothing can escape from it. Right. It turns out Schwarzschild died soon after in the war. And so he never saw the paper being published. Einstein published it for him and named it after. So we call this the Schwarzschild radius. But the person who actually showed how to do this, Schwarzschild didn't tell you how to do this, how to actually shrink a star into something that can form a black hole, which is what we call it now. The person who did it was Subramanian Chandrasekhar, who read this kind of work as a student, as an undergraduate at Trinity, at Presidency College in Madras, and then went over to Cambridge to work with Paul Dirac. And before, on his way, he had read a few papers on astrophysics, as well as been familiar with become familiar with the new subject of quantum mechanics. How did he know that? Because in the 1920s, very few people knew about quantum mechanics. It turns out his uncle was C.V. Raman, who was working in Calcutta at that time, and he used to visit his uncle, his mother's brother, quite a lot. During his visits to his uncle, he learned about this thing about quantum mechanics, and he realized that if you apply the laws of quantum mechanics to the general theory of stars, stars being balls of gas, very high temperature, actually undergoing nuclear fusion in the middle, something that was not very well understood in the 1920s, the nature of the nuclear reactions that gave out the light from stars. But Chandrasekhar did a lot of work on that, and Chandrasekhar worked out that as the star collapses, then it can actually, due to quantum mechanical requirements of the particles which form matter, which essentially are Fermi-Dirac particles, then it leads to certain constraints that will stop the collapse of the stars collapsing at the end of their nuclear burning life. And the stars that collapse might actually form things that are of the size of a few kilometers. Neutron stars, the white dwarfs, with white dwarfs are a few thousand kilometers across. Neutron stars are 10 kilometers across. Or if things are much more massive, it can go into a much, much smaller size. And it can go beyond, for the sun being 3 kilometers, higher mass stars, the Schwarzschild radius is maybe 10 kilometers, 20 kilometers, something like that. So this is possible. So Chandrasekhar showed that. Now, all this was based on the fact that, that Einstein modified our notion of gravity. And this is something that one must understand if one has to understand the nature of black holes that I'm talking about. Newton said that the force between two massive particles acts along the line of sight and is the gravitational force, gmm over r squared. Einstein, from the very beginning, realized that one has to think completely out of the box in order to figure out what happens if things are moving very fast and things are very massive. Because Newton's basic concept does not work. I mean, for example, as a young kid, Einstein worried about things like, in fact, he wrote at the age of 15 a paper for his uncle, who's a physics teacher, asking this question: if there are two things that are traveling very close to the speed of light, then, for example, there's a force that acts in between them. How does this particle know which direction that force is coming from? Because it takes a certain amount of time for the information to go from one particle to another, as to it's being pulled or it's pulling something. But by that time that information has reached this other particle, this one would have moved, right? So does this particle know which direction it's being pulled? It's a very basic question. Now, for Newton, this was very simple. Newton thought everything was instantaneous, but by the time Einstein had come to the scene at the beginning of the 20th century, it was well understood that information cannot travel at infinite speed, right? And one of the first things Einstein had done in 1903 is publish the special theory of relativity, in which he had said that nothing can travel faster than the speed of light. Having said that, then this question became very important, that you cannot really have gravity as a force which acts at long range. And so Einstein started thinking about doing something that is very local rather than long range. And Einstein then said, actually, gravity is nothing but the change in the curvature of space and time due to a massive object. So gravity is not a force. Things move naturally along paths along curved space-time, and space is curved according to the mass of objects. So here you are, here's the sun, and the Earth is moving around the sun, not because the sun is pulling the Earth due to an invisible string, which is what we are taught in school. I don't know why people don't teach in school Einstein's view of things, because that's the right one. The sun, due to its mass, has deformed space around it, and that's shown by the green thing. You can see the Earth also has deformed space around it a little, but not as much. And the Earth goes around the sun because it's trapped in that deformed space-time, right? And thus, you can also explain how light can bend and light can travel, because light doesn't need to be massive. In the Newtonian sense, light also follows the geometry of space-time. And if space is curved, then light's trajectory is also curved, right? So that's Einstein's idea of gravity. And so if thus anything massive curves space-time, and if you take mass and you make it smaller and smaller, then the curvature of space would also become larger and larger. And you can see that if you take the same star and squeeze it to a very small volume, then space-time will be curved a lot. And then for light to come out of that highly curved space-time, it's going to take a lot of energy. And after a while, after a certain point, even light or anything cannot have that kind of energy to come out of that very curved space. And that is what a black hole is, right? So you can see it very naturally follows from Einstein's formulation of the nature of gravity. I hope that's clear now. So here you are. So I've gone back to this idea of the earlier slide I had, just putting down some numbers, and you see that for solar mass, it's 3 kilometers. So how would you actually see a black hole? So this is a picture of a black hole, right? That's the main challenge. Nothing comes out of a black hole. We see things because we actually either bounce light of something, or we see the light. And by light, I mean all kinds of radiation. It could be X-rays, it could be gamma rays, ultraviolet. Something has to come out of it, for us to see it. And if nothing comes out of a particular object, you can't see it. And this is why for a long time, there were people who believed that nobody can find a black hole. In fact, when I was a student in the 80s, I was a student, I went to a course by Stephen Hawking on black holes. And I was one of his students. And then, even then, he was very openly saying that he could bet anybody, and he had all these bets with famous people about black holes not being visible, and you really cannot see black holes. So this whole talk is about how you can find black holes. And the kind of stuff that I'm going to talk about today, and I'm talking about today, actually started happening in the 1990s. And Stephen Hawking conceded defeat in his bets. And I think these bets were, it's not that he didn't believe in it, but he was, I think, trying to urge people to go and find these things. In the 90s, Hawking conceded defeat in some of these bets that he had with various people, particularly starting with the Kip Thorne one. As you know, Kip Thorne would later earn the Nobel Prize for discovering gravitational waves, but that's different. Here's, before I start talking about the other things, I just wanted to also say, as I said at the beginning, you should not be afraid of black holes. Black holes are not things that go around sucking matter in. Actually, very far away from black hole. The gravity of the black hole is very similar to a normal matter. There's nothing special about black holes. If the sun today turned into a black hole, and it won't, that's not what the sun is going to turn into. But if it did, then nothing would happen to the Earth's orbit. Actually, it'll become very dark because all our light comes from the sun. But other than that, the Earth will continue going around the sun because the gravitational pull of the sun turning into a black hole won't even reach the orbit of Mercury, just about maybe, because the actual gravitational effect of a black hole, you can think of it in terms of that very deep trough that goes in, is so just outside the Schwarzschild radius, which is really the event horizon. You can't see anything inside, but even outside, the really strong gravitational pull extends to maybe 100 times, if not a little more, than the Schwarzschild radius. Remember, the sun's Schwarzschild radius is 3 kilometers, so that's very small. So it doesn't extend to very large numbers, very large multiples of that Schwarzschild radius. So you really have to go very near a black hole to get sucked in. Now, how do we see black holes? Black holes, there are many kinds. You have the stellar mass black holes, the black holes that are a few times the mass of the sun. And then you have black holes that are supermassive black holes, which are many millions to billions of times the mass of the sun. So these are the two kinds that I'm going to talk about today, but there has always been some notion that there might be black holes that are in between, because if you really want to form the supermassive black holes from the stellar mass black holes, then how do you get there? And if you get there by going continuously through merging black holes into bigger ones, then you should be able to see things in between. And towards the end of today's talk, you will see that we've only started looking at actually finding black holes that are of intermediate mass. And people really didn't believe that these things existed till maybe 2 or 3 years ago. And there was a lot of controversy in the astronomical literature about whether the mid-mass black holes exist. So here, let's begin with the black hole in the middle of our galaxy, which has been so much in the news this year because of the Nobel Prize. So that's a supermassive black hole right in the middle of a galaxy. This is what our galaxy looks like. If you look at it face on, this is what it would look like. And if you're looking at edge on, you'll see that it's a very thin disk with a little bulge in the middle of stars. The sun is about 8 kiloparsecs, which is like 25,000 light years. A kiloparsec is 1,000 parsecs. A parsec is 3¼ light years away from the center of the galaxy. And that's where we are. We look at the sky from this vantage point. So the stars, all the stars that we see in the sky are essentially within this kind of a little band, little disk in the galaxy, and then outside we don't really see any stars. But because we are in the northern hemisphere, we see this part of the Milky Way, and so see all the stars. But if we are looking towards the middle of the Milky Way, then you can see a band across the sky of stars, and that's why it's called the Milky Way. In many Indian languages, we call it the Akash Ganga, the river in the sky. It looks like a river of stars, and it's much better seen from the southern hemisphere, the center of the galaxy. And it's right in the center of the galaxy. There lies Sagittarius X1, which is the center of the Milky Way. Sagittarius A star, which is the central black hole of the Milky Way. And for a long time, we see a supermassive black hole in the middle of all galaxies. So we knew there's always there's one in our galaxy. And so the question was, how do you find it, prove its existence, and quantify its mass? And looking towards the center of this galaxy, you can see that there are two big challenges. One challenge is that if you look at that, this is an artist's impression, of course, you can't take a picture of our own galaxy being within it. But what it's showing is that in the plane of the galaxy, and we lie in the plane of the galaxy, we're looking towards the center, there's a lot of dust, that black stuff. That dust comes from the leftovers from when the stars were made, but also comes from the stuff that comes out of stars after stars die and go supernova. And the material comes out and then goes into other stars and stuff like that. So all that, because in the plane of the galaxy, there's a lot of newborn stars and stars that are going supernova. All that's happening in the center of the central plane of the galaxy. There's a lot of dust, and that dust actually obscures light in the visible range. And this is why you see it. Actually, you see it. You take a picture, you see it as opaque stuff. So in order for us to, from the sun, from the Earth, look towards the center of the galaxy and try to find things around the black hole, it's challenging, right? Now, what are we trying to do here? What we're trying to do here is to figure out, because we'll never see the black hole in the middle of the galaxy, right? But what we can do is we can look at stars around it. And if you can look at stars very close to the galaxy, from their motion, you can infer what they're being pulled by and infer its mass. It's very similar to trying to measure the mass of the sun by looking at the orbits of the planets. If you take Earth's orbit or Jupiter's orbit, from that you can easily, balance centrifugal force and gravitational force and find the mass of the sun. Similarly, if you look at stars going around the central black hole, then from their orbits you can find the mass of the black hole. But to do that, you have to give up trying to observe these stars in the optical band because you have this dust. And then there's a far more important problem. So we're looking towards Sagittarius A star, which is where the black hole is. You won't be able to see the black hole. Remember, it's a very tiny thing there. But there are lots of stars. There's a star cluster in the center of our galaxy. So if you can go into that and then look at now here, what you're doing is you are actually observing this particular star cluster in the infrared. This is the near infrared. We observed 2 microns, which is far above the limit that our eye can see. Our eye can see up to 0.8 microns, 800 nanometers in wavelength. And so at these wavelengths, the dust becomes transparent, and then you can look through. So that's one technology that one had to overcome. And the second problem, so what you're trying to do is to look at the stars and look at how they're moving in 3-dimensional space and try to figure out the mass of the object that's pulling them. The other problem is that how close you want to get to the supermassive black hole. And in order to do that, you need very, very good resolution. And this is a problem that has plagued us, astronomers, for a long time. Stars twinkle. And why do they twinkle? Because as the light comes through the atmosphere to us, it comes through various layers of the atmosphere. And all the layers of the atmosphere of the 100 kilometers or so the atmosphere has a different temperature, pressure, density, and they're changing all the time. A matter of seconds, it's changing. Now, the refractive index depends on temperature, pressure, density, all these parameters. And if the refractive index is changing as a function of time, on the time scales of seconds or even less, then as the light comes in, as you can see, its path before it reaches you or the telescope goes through various zigzag, and then if you have an image of a star that's formed at the focal plane of your telescope, it's going to dance around. And this is why, when you look at a star, it twinkles, because the image dances around. Now, if you want to take a picture, then it's going to be blurred, because the picture takes a long time for you to form that image, and during that time, this image would have gone around. So this effect you have to get over, and the Nobel Prize this year was essentially for using this technology rather than the black hole, because you had to actually use the technology to overcome this, to see these stars. So you look at the actual numbers. If you want to measure the size of a star, say take the sun and take it to the center of our galaxy, which is 25,000 light years away, 8 kiloparsecs away, the angular diameter of the sun is going to be a micro arc second, right? And this effect blurs things to about a second of arc. 1 arc second, remember, is 1/3600th of a degree, right? 3,600 arc seconds make a degree. So it just blurs things, and the size of a star, size of a sun, at the distance of the galactic center is 1/1,000,000th of that. So then if you want to look at the Schwarzschild radius of the central black hole of our galaxy, that is also of that order, 10 to the power -5 arc seconds, right? And the separation of stars near the center of the galaxy is of the order of 100th of an arc second. And yet our atmosphere blurs things to more than a second of arc. So it's impossible to actually resolve the stars that are going around the central black hole and measure their motion. But this is what the people who got the Nobel Prize this year did. One of the groups used the Keck telescopes in Hawaii. And the way the Keck telescopes work is that the telescope, which is 10 meters across, the largest telescope in the world, actually has 36 different segments, hexagonal segments, making up the 10-meter telescope. And each segment of the telescope can be moved with respect to each other, computer controlled, in real time. And then the telescope, this is called adaptive optics, the telescope knows by looking at a smaller telescope and looking at a point object in the sky, how the atmosphere is changing, how the images are being moved around, and in real time communicates that to the telescope. And the telescope, the computer controlling the mirror, the primary mirror, changes the shape of the mirror in real time to keep the focus sharp. And this has been achieved in the last 20 years, right? And it's called adaptive optics. It's absolutely fantastic. It makes the wavefront, keeps the wavefront parallel, and thus you can see the blurred images. You can actually resolve individual stars. And this is what the galactic center stars look like. Galactic center 2.2 microns. With a normal big telescope, the biggest telescopes in the world, is a blur. You won't be able to see anything. Of course, you can't see the black hole, but you can't see the stars and differentiate them near the black hole. But here it is on the right-hand side with adaptive optics that works on the Keck. You can see the individual stars. And this is what these two people did. Actually, Reinhard Genzel and his group worked with this set of telescopes, the 4 VLTs, the very large telescopes in Chile, which are 8-meter class telescopes that also have adaptive optics. And Raychaudhury's group at UCLA used the Keck telescopes in Hawaii, the 2 Keck telescopes, to do the same thing. And they started in the 1990s. And here, day after day after day, night after night after night, they started looking at the stars that are around the black hole in the center of our galaxy. And here are, here's a movie made up of this. And you can look at the date on the top right-hand corner, and you can see that these are actually real images made day after day, movies made out of them to show the motion of the stars. And if you look on the right-hand side, that line represents 1/10 of an arc second. As I said, normal without adaptive optics, this whole thing will be a big blur. You won't be able to see anything. But as I said, the nearest S2, for example, comes to the black hole's position is 1/100th of an arc second, and they are able to resolve this. So just look at these, how exquisite these stellar orbits are. Starting from 1995, this is Andrea Geze's group, and then Genzel started in 1992, and they mapped out the nice elliptical orbits of all of these, just from S2, which is one of my favorite stars, and goes around the black hole. You can see that you can't see the black hole. That's the central position of the black hole. It lies at the focus of the ellipse, and you can just use normal, you can see the lovely elliptical orbits that they measured in the last 20 years by monitoring these stars every night using adaptive optics. You can use something like Kepler's third law and find the mass of the object, the relativistic version of it, not really the simple version. And we now know that that's the position of the from this particular orbit S2, but you can have an independent thing from all the other stars, that the mass of that black hole is 4 times 4 million solar masses. Now, how do I know it's a black hole? And that's because of size. If you take a star cluster that has 1 million stars, that would also have a mass of 1 million solar masses. But the size of that will be about at least about 30 to 40 to 50 light years, right? Here you can see the star is going so close. This is the perigalacticon distance, which means that that's the distance that's going to near the star is about a little more than the size of the solar system, not 50 light years. So it just shows that if that were a star cluster, then S2 or any of these stars going very close to the black hole would have collided with it and not gone past it. And so it just shows that you have 10 to the power 6 times the mass of the sun, all in a small volume, and this volume is very small, and it can only be the volume of a single star. And it turns out the Schwarzschild radius of this black hole, of that mass, is of the order slightly larger than the size of the current, our sun, that is 12 billion kilometers. So that is how they established that there's a black hole in the middle of our galaxy. So here you are. Here's one way of finding supermassive black holes. I told you that there are many kinds of black holes, and I'm going to talk about ways of finding stellar mass black holes next. And there are many ways of finding black holes, but I thought I'd select a couple and talk about how we can find the most abundant black hole. That is, every galaxy has one supermassive black hole in the middle, but all galaxies, including our galaxy, has hundreds of thousands, maybe millions of stellar mass black holes. How do you find them? So here you are. So normally, stars like to exist in pairs. In fact, in our galaxy, more than half of the stars are in binary systems. Stars, and of course, if you have a planet around them, you see two suns in the sky, like Tatooine in Star Wars. So actually, that's more common. Our solar system has only one sun. Actually, Jupiter could have become a sun if it were about 10 times bigger, but it didn't. And so we are stuck with one sun. Right. So now, if you have a binary system in which there are two stars, one star will be larger than the other in terms of mass, right? Now, in astronomy, we know that stars, the lifetime of a star is very crucially dependent on its mass. Bigger stars or more massive stars, there's a high power of dependence on lifetime, on mass, which means that the very big stars burn up their nuclear fuel fast and end their life in terms of nuclear burning. And so at the end of nuclear burning, what happens to stars is that they lose, because their equilibrium that is held during their lifetime when nuclear burning is happening, gravitation is countered by the amount of heat that's coming out from the center of a star, and they balance each other. Once that central engine that's producing the heat goes off, then the star goes out of equilibrium. And if it's a massive star, it goes boom, it goes supernova, the outer layers are ejected, and the central bit then collapses. And we know from Chandrasekhar's work that if the star has a mass that's more than about 4 or 5 times the mass of the sun, then the remnant in the middle becomes a black hole. So just imagine that. I'm not going into that whole picture of stellar evolution. This talk is not about it. So imagine in a binary system, the more massive star has now gone supernova and has left behind a black hole. Now we have a binary system in which there's a normal star and there's a black hole, and they're orbiting each other, right? Now, very soon meaning a few million years later, a few hundreds of millions of years later, whatever, in astronomical timescale, very soon, the other star is going to start evolving as well, and it'll stop, its nuclear burning in the middle, and as a result, it's going to grow larger. It's out of equilibrium, and as it grows larger, it becomes red, and its outer layers will have far less gravity attracting it towards the star, and there the very nearby black hole can start pulling out the outer layers of the other star towards it. Now, stars are rotating, which is what I haven't shown that here. Since the star is rotating, the matter that comes out of the star has angular momentum, and so it's not going to go right into the black hole. It's impossible to destroy angular momentum, so it's going to go and spin around the black hole. And as a result, it'll form a disk, which is called an accretion disk. Now, disk will stay there for a long time, and due to friction, it'll lose the angular momentum, and slowly it's going to sink into the black hole, the matter. But the black hole can be there. You don't see the black hole, but you can see the accretion disk, and this accretion disk will get very hot because it's very near the black hole. The black hole's gravitational potential energy is going to make it very, very hot. Now, this artist's impression, you see that the black hole itself, you don't see what's inside, but you can see this immense gas turning around the black hole, and they get very, very hot. And once something gets very hot, these things go up to 10 to the power 7 degrees, 10 million degrees hot, they start emitting X-rays. So what you'll do, so in these binary systems, the lesson is to find black holes, you need to look at things that are emitting in X-rays. So where are these X-rays? So you can see that in this entire electromagnetic spectrum, as you know, we were talking about visible light when we talked about, and then we talked about infrared. X-rays are of wavelength nanometers, and their energies can be kilo-electron volts, very, very high energy. And so how can you actually find these things which are so energetic? The other problem is that if you look at the transparency of the atmosphere along the electromagnetic spectrum, here is the visible in the middle, and there's a little window, and this is why you can see, you know that stars exist, because our eyes can see the light that can come through the atmosphere. But most of the other kinds of light can't come through the atmosphere. It's a coincidence. You have to think about that. It's the way we have evolved as species, that we can see stars. Our eyes are sensitive. If our eyes were sensitive to infrared, then we wouldn't have known that stars exist, right? Because all that stuff is stopped by the atmosphere. And it's good that X-rays are stopped by the atmosphere. It's stopped by the ozone layer, actually, X-rays and ultraviolet, because that would be harmful for our skin. But this also means that you can't see the accretion disks around black holes because they emit X-rays. So the lesson is that you have to go into space. So we had to wait till we could launch telescopes into space that are sensitive to X-rays. So here's something I worked on quite a bit for NASA, working at Harvard, building the Chandra X-Ray Observatory, which was launched in 1999. And you can see this is a very interesting telescope, and I'm going to tell you why it is interesting. And that's, first of all, it's got this very unusual orbit. Because the Earth is surrounded by radiation belts that have very high energy radiation. This comes from the particles, charged particles that are trapped by the Earth's magnetic field. Charged particles come from the sun. And so for thousands of kilometers, tens of thousands of kilometers, these things are there. And so if you have a satellite going around outside the atmosphere, but inside these radiation belts, the Van Allen radiation belts, then they only see the radiation, the X-ray radiation that's coming from the charged particles. They don't see anything outside. So you have to send them very far away. So Chandra X-ray telescope has this orbit of 64 hours, not like the space station, which has a 90-minute orbit. And it goes far away and then comes back. And it's only turned on when it's 60,000 kilometers away from the Earth. And so it works for about 30 hours of those 60 hours, right? But then there's another important thing, and that is to image X-rays. How would you image them, right? Because you know that if I throw an X-ray towards you, it's going to go right through you. So you focus light by normal incidence, and light bounces off a surface and then forms an image. You can't do that with X-rays. They go right through. So how do you do that? Now, India has a similar, I talked about Chandra, which is a NASA telescope. We launched AstraSat 5 years ago, and it has 3 X-ray telescopes on it. It's got 5 telescopes. One is a very, very successful ultraviolet telescope, actually the best ultraviolet telescope in the world. And we have amazing X-ray telescopes also on AstraSat that are doing the same thing. Now, how do you reflect X-rays? See, think about it. So think about this being a railing with gaps. And what you're doing is you are essentially, my animation doesn't work, but think about you're throwing a football at it. And the football is larger than the railing, and it'll go and come back. And this is what happens in light. But if you throw a little cricket ball at it, it'll go right through. Okay? So the way to do it is to reflect it, is to turn the railing around, such that if you actually throw the cricket ball at an angle, if it's a very small angle, then the chance of it hitting one of the railings and coming back is much larger, because the effective gap between the railings has become very, very small because it's turned around. And that's exactly what we do for X-ray mirrors. In X-ray mirrors, you have the X-rays actually fall on the mirror at a very small angle, which we call grazing incidence. rather normal incidence. And you can see as a function of grazing angle, which is 2 or 3 degrees, if you have a gold-plated mirror, then it gets bounced off. And if it's more than 2 or 3 degrees, it will go right through. So the mirrors are built such that nowhere does the light that's coming, the X-ray that's coming, is more than a couple of degrees from the surface. And you do that, I don't know whether this will work. Somehow it doesn't, but it just shows that in the Chandra X-ray telescope, you can see that the mirror is very long. And so as the light comes in through here, it's slowly reflected in small angles, and it takes them, so that's why the mirror is very long. It's 5 meters long, and takes them to the camera which detects them. And it can produce exquisite images as good as the images in the Hubble Space Telescope, but in X-rays. And then that's how you can actually image these stars. Now, because they are being reflected in such a way, you can nest them. And Chandra has, for example, 4 concentric systems of mirrors, which can independently do this, and you can detect more and more X-rays. This is the mirror system from AstraSat, our Indian telescope, at the soft X-ray telescope. And you can see in there how many mirrors we have. We have about 20 or so mirrors that are nested together. And they form images of X-rays. And so that was launched about 15 years after Chandra. And we do this amazing imaging. Now, here you are. So let's give you an example of how this works. What we're trying to do is we're trying to take the black holes in the system and trying to emit, and it's emitting X-rays, trying to detect these things. Here's an example. Here's a nearby galaxy called Centaurus A, which is outside the Milky Way. It's about 5 megaparsecs away. And it's the nearest galaxy with a very, very big supermassive black hole in the middle. In fact, the supermassive black hole right in the middle of this galaxy is 1 billion times the mass of the sun, a few billion times, not 1 million times. It's the nearest elliptical galaxy. And it's got this nice dust lane in the middle. And it's got, so this is an optical picture of it taken with a small telescope on the Earth. And you're seeing a picture of it at optical wavelengths. Now, when you see something with optical wavelengths like the sun, with the eye or a telescope, you are seeing it because our sun's surface is 6,000 degrees hot. So if it's a few thousand degrees hot, all stars are black bodies. It's the peak of its emission happens in the visual wavelength, right? So everything that you see in this picture is about a few thousand degrees hot. In order to see the accretion disks around black holes, you'll have to have a similar picture, but everything will be there 10 to the power 7 degrees hot. So this is what we did. We took Chandra and aimed at this particular galaxy for 1 million seconds, and this is what we got. Same picture, but with an X-ray telescope. So here you are, optical. Here everything is at least 10 to the power 7 degrees hot, 10 to the power 3 degrees hot, 10 to the power 7 degrees hot. And what do we see? We see this immense, huge blob in the middle. That's the supermassive black hole. It's actually emitted a huge jet of X-rays emitting plasma, which is being flung across, and that's a result of the supermassive black hole being very greedy, trying to eat a lot of matter, but it can't actually take it in. But around it are all these little point objects, and these are all accretion disks in binary systems of stars. And these accretion disks are 10 to the 7 degrees hot and happen in 2 ways. One is a neutron star, and the other is a black hole. In fact, I had a student who worked on all these little point objects for his PhD and concluded that there are 5 of these are black holes. That one, things like that. And you can model them, and you can find out that these are stellar mass black holes, a few times the mass of the sun. Okay, so this is one way of finding them. And I'm going to carry on, if I may. Is it all right for another 5 minutes? Because I'm going to talk about a little bit about another way, and then I'll come back and take people's questions. Is that all right? I can see John be there.
Yes, so you can go on for another 4 minutes.
Okay, so this is one way of finding stellar mass black holes. But the more exciting thing now has happened is that one can find these things in a very different way. And this so for example, from Chandra, we know that the smallest black hole that we found so far is about 3.8 times the mass of the sun. If it gets any smaller, they become neutron stars, not black holes. We know the nearest one we have found is about 1,600 light years away. So you need not be afraid. Very, very far away, the nearest black hole, and it's about 10 times the mass of the sun. Now, I said that we have stellar mass black holes and supermassive black holes, and there are mid-sized black holes that are being discovered. That is now coming out of what is called LIGO. And you'll hear more about LIGO tomorrow from Bala Iyer's talk. But I mean, we have gotten involved in India. We have gotten involved in these huge science projects for the first time. When I was a student, I envy you because the people who are coming up and at the beginning of their career now, a lot of you are, you will be able to work in India with Indian facilities that we did not. I knew that if I had to work with a world-beating experimental facility, I had to go abroad. That's why I went abroad and worked abroad for a long time. Now India is a partner. I just came out a few minutes ago from a board meeting of the 30-meter telescope, which is India's being built in Hawaii. We are building a gravitational wave observatory in India, the square kilometer array, et cetera, et cetera, et cetera. And I'm going to talk quickly about how that's relevant to my talk. 30-meter telescope that's being built in Hawaii. Indians are part of this. It's just the large version of Keck. Keck you saw has 36 mirrors, about 1 meter size, forming a surface that's 10 meters across. The 30-meter telescope will have 492 mirrors, same design, very similar place. It's not far from the Keck telescope. And it's being built by 5 countries. Japan is a 20% partner, India is a 10% partner. We're actually building it, not just actually funding it, but building it. Almost all the mirrors are being polished in India. The entire software is being written in Pune. And the actual control segment, the control system that's going to control each segment to make the mirror, which will be adaptive optics, is being built in India by Indian engineers, Indian engineering firms. So Andrea Ghez, for example, who got the Nobel Prize this year, is part of this because her university is part of this part of the US. And I meet her always on these board meetings of the TMT. And her interest in this, for example, is that this is just a bigger Keck. So she can do the same thing with lots of other stars around our black hole, but also look at other galaxies. So the TMT, the 30-meter telescope, will be one of the biggest telescopes in the world. It will be aiming at about 2033, 34. So that's 10 years from now. And it's going to work a lot on different kinds of black holes all over our galaxy. But the most important way of studying black holes now, and I'm not going to talk much about it because Bala Iyer is going to talk about this tomorrow, is gravitational waves. This is completely outside the electromagnetic wave spectrum. Gravitational waves were first discovered in 2015, announced in 2016. As you know, in the paper that announced them, 1,000 authors and 40 of them were from India, working in India, and 10 of them were from my institute here at IUCAA in Pune. And this is somewhere Indians are very, very involved in. Einstein's theory, which said that actually gravity means that space-time is curved, also came up with a prediction that if things move in space-time, then the entire space-time vibrates, just like ripples happen when you throw a stone in water. And these ripples in space-time then propagate as gravitational waves. Einstein predicted that there's no way people can see it, because even for the most massive objects in the universe, the ripples would have a displacement, an amplitude of which is smaller than the size of the atomic nucleus, and this cannot be found. And what was found in 2015 was the merger of 2 black holes. Black holes if they are in a binary system where both stars are black holes. Before this, I talked about a normal star and a black hole. But here you have two stars that are black hole, and they can actually go around each other and finally merge. They cause a huge disturbance in space-time, which was something that was detected by these two observatories. And these are essentially, I'm not going to go into the details, tomorrow you'll hear of them. Gravitational wave observatory is just a big Michelson spectrometer, 4 kilometers on each long, and these two are in the US 3,000 kilometers apart, and they actually detected for the first time. And since then, we've detected 50 such events and many more, probably the 50 confirmed events. And what happens is that within a few seconds, you can see this is the first detection that was done in September 2015, where two of these black holes were found to merge within, if you see the x-axis here, half a second, essentially. And it sent out this waveform that as the black holes came closer and closer and merged, the frequency of the gravitational wave went up. You can see frequency is a function of time. It's called a chirp, like the bird's chirps. And that's a characteristic thing that you're looking out for merging neutron stars or black holes. It led to all kinds of popular appeal. And what we had discovered, and these are as one of my students did this wonderful plot in which you can see that the Schwarzschild radii of the black holes that were found, of course, the size of some states, right? It was like about 30 times the mass of the sun, each of these black holes merging to form something that was about 62 times the mass of the sun. So one was 36, the other was 29, and they merged together and formed a 62 solar mass black hole. And if you look at the difference, the amount of mass that was lost as energy of the gravitational waves, mc squared. But the interesting thing is, and you'll hear the story tomorrow from Professor Iyer, but the interesting thing is, of the 50 that have been discovered now, if you look at the masses of the black holes, well, I said that the first one that was found was this one, of 230 or so times the mass of the sun, forming something 60 times. Sorry, it was the first one was this one. But now you can see that in the last year or so, we've found black holes that are more than 100 times the mass of the sun, many of them. The latest one that was announced as things that are 80 times the mass of the sun merging to become 140 times the mass of the sun, right? So we are finding these black holes that are so much bigger than the ones we found before. And I'm almost to the end, but just showing how you can see, compare the black holes that were found by X-rays, which are a few times, here's the times the mass of the sun number. And you can see 5 times, 6 times, 7 times, 8 times the mass of the sun. Those are the things you're finding, the purple ones, through X-rays like Chandra and AstraSat and others. But now, with the gravitational wave instruments, you can find things, and for each of these, you can find 3 black holes. 2 black holes merge into one in a gravitational wave thing, and you can go up to all the way up to 160 times the mass of the sun. So the more massive ones, and we're climbing this mass ladder now, and hopefully we will fill up the gap between the stellar mass black holes and the supermassive black holes. And this is relevant because we are building a LIGO in India. The third one, I showed you the 2 in the US. The third one will be built here in Maharashtra, near Hingoli, near Nanded, about 10 hours drive from here in Pune. And it'll be built entirely in India. It'd be wonderful. We are just waiting for the government to sanction the money. The land has been bought, and we are waiting for the pandemic to be over to start building it. It'll take us about 5 to 6 years to build. And hopefully from about 2027 onwards, we will have a gravitational wave observatory on Indian soil with anybody. And here we need more engineers than physicists because we have to build this thing. And so looking for people to get interested in this kind of facility, right? Just last slide, with some books that you might want to read if you want to know more about black holes. Kip Thorne's book is one of my favorites. Talks about time warps and black holes, the interface between science fiction and science. As you know, he he was a major force behind the amazing graphics in the Interstellar movie, for example. And if you want to know about wormholes and stuff, try and find Richard Gott's book and read a good biography of Einstein. You'll know how he came up with this great idea. I'll stop there and see whether we have questions. Thanks very much. Over to
Thanks a
you.
lot, sir.
Yeah.
Yes, sir, we've got a lot of questions. I just wanted to clarify one point though. Dr. Bala Iyer's talk has already happened. It happened yesterday at
Okay, fine.
Yes, sir. And he did discuss all the different topics that you mentioned, the 7 millisecond difference, time distance between the two observatories in US, and the detection of the clear detection of intermediate sized black holes through the merger. All of that has been discussed and it happened yesterday. And now I guess we'll go on to the questions, which there are a lot of as of right now. Yes, so the first question would be from RFS. He's asking why is the surrounding of black hole? I think he's asking about the accretion disk. Why is it so immensely hot? Are reactions happening over there?
Okay. It's hot because if you take something, if you think of thermodynamics of things, if you gravitational energy itself comes from the potential energy that is due to the gravitational attraction of two things, right? So if two things attract each other with a force of gravity, then as you know, the force is gm/r squared, but the actual potential energy is minus gm/r, right? And so the gravitation itself has an energy associated with it. And so as r becomes small, things come closer and closer together. The gravitational potential energy, which is negative, so it is getting larger and larger, right? Now, on the other hand, kinetic energy, which is related to temperature, is quantified by the random motion of the particles that constitute matter, right? And essentially in physics, what happens is that there has to be a balance between the potential energy and the kinetic energy. There's something called the Virel theorem, which says that the kinetic energy and the potential energy together have to be constant, right? So twice the kinetic energy plus the potential energy is constant. That's the theorem. So what happens is that as something is getting closer and closer to the black hole, it is acquiring the gravitational energy due to the black hole because its gravitational potential energy is getting higher and higher. And as a result, its kinetic energy is also getting higher. Okay? And the higher the kinetic energy, the higher the temperature. Temperature is related to kinetic energy. Normal thermodynamics, kT, is related to half mv squared. Okay. So something can get very hot by coming very close to something that's pulling it with a very high force. That's the idea. And this accretion disk is very hot because its amount of matter, which is in the immense gravitational field of the black hole, very close to it. When you're very far from it, your gmm/r is very small, whereas your gmm/r is extremely large if you're very close to the black hole. And this is there's no chemical reaction or any reaction going on. It's just the potential energy being converted into kinetic energy, and kinetic energy giving you its temperature. So the random motions in this plasma or in this matter becomes much larger because of the gravitational energy, and that is the temperature. That is the index of the temperature. I hope that makes sense to you.
Right, sir. Now Deep asks, if there exists some universal wave function determining everything, wouldn't the expansion of the universe bring about changes in it? And if so, wouldn't it change the entanglement entropy between inside and outside of the event horizon and hence affect the radiation from the black hole and hence its temperature?
Right. So what you're talking about is completely controversial and not even worked out. Nobody, even Hawking tried to do this. Hawking tried towards the end of his life to figure out how to entangle the information inside a black hole to the outside. And to some extent, it depends on a formulation of quantum gravity. This hasn't happened yet. So it's a very interesting question, but it's a completely open question. Nobody knows how to write down a quantum picture of a black hole, right? So I'm not even sure what a universal wave function of the universe would be. We don't know it. There's no knowledge of it. Having said that, there are there's quite a lot of work done on this. People haven't converged on it just because, for example, think about how do you quantify the entropy of a black hole? If you write down the entropy in terms of normal information theory, log of the number of states available, energy states available, stuff like that, then you would find that the entropy of a black hole is many orders of magnitude more than anything else in the universe. And so people have said, does it even make sense? If you, for example, write down the entropy of everything in the universe, you'll find black holes one black hole can account for more entropy than everything else in the universe put together. So it is clear that using classical analogs, we aren't really understanding the quantum implications of a black hole. Similarly, Hawking radiation, which is another quantum effect associated with a black hole, which doesn't have a classical way of looking at it. So, so the bottom line is that a quantum definition of a black hole has not emerged really. That's probably one of the biggest breakthroughs that's going to come in this century. We're waiting for it, but we don't know. Anyway, next.
Another question from Deep. Is there any effect on the relativistic precision of the stars on determining the black hole's mass and position?
Right. So you're good question. The picture I showed you of the Kepler's laws, etc., actually needs a lot of relativistic corrections to get it right. They're not sometimes big corrections, but they're corrections. Now, in the calculation I showed you in the middle of our galaxy of the supermassive black hole, the relativistic Kepler's law actually works quite well, and you have to take into account gravitational redshifts and all kinds of things to get that right. And it's done in any of their papers you can look up, very nicely done. There, the corrections are not huge. Precession comes really become important in the case of binary systems. And for binary black holes, for example, where you do the calculation for the merging black hole calculation for the gravitational waves, or you do the calculation for the binary system for the X-rays, where you have a black hole or a neutron star together with another star. And there, the orbit's precession becomes very important. So if you're looking at, for example, an X-ray binary in which you have a galaxy, a star, and a normal star and a black hole, as I said, we worked out on all the little binary objects that you saw in the Centaurus A picture. There, what you're trying to do is you're trying to quantify the orbits by looking at the variations in the X-ray intensity as a function of time. I didn't talk about all that today, but the way you establish whether something is a black hole or a neutron star is you look at its temporal variation. So you observe it for a time and you see how it's varying. And there you have to make all kinds of relativistic corrections, general relativistic corrections. Precession is one of them. Something called the lens-thinning effect, for example, which is very interesting, which comes from the frame dragging of space-time itself, and things like that. There's something called the Shapiro effect, which is an extra Shapiro triangular, which is also a general relativistic effect and things like that. So all that comes in, yes. Anybody else?
Right. Yes, sir. The next question would be from Bhavya Bhatt. He's asking, what is the current status on solution of black hole information paradox? And what are your views on the current approaches to the problem based
Yeah,
on...
but,
a-
this is very similar to what I said before. It's the same question, essentially. The information paradox and the entanglement between the wave functions of inside black hole and outside the black hole. How do you quantify the information inside a black hole? As I talked about the entropy of a black hole, all there, and the current status is not much is being done really. I mean, people are trying to understand. Hawking's final papers were on this. I have a colleague here, Padmanabhan, who works on this. Wonderful work is being done, but it's a completely unsolved problem, and I don't think we are even close to figuring out how to quantify the quantum states in a black hole. So it's a very open subject, and it's wonderful area of research, and a lot of people who are your colleagues right now would be working on this kind of thing when they start their PhD now. I've got several students here in IUCAA who work on this kind of problems.
Yes, sir. Now a question from Prashant. He's saying that he's seen somewhere that X-rays contain the information of your past, meaning we could see the past of a planet or of Earth or someone through X-rays. Is it possible? If yes, how?
No, I mean, I think he's talking about astrology or something, or I'm not sure. No, it's absolutely wrong. In astronomy, one great thing is that you can see the past of the universe because you are looking at something, information that's come through radiation to you, that's come from very far away, and it's taken a long time to get to you. So if you're looking at something very far away, you're looking at it as if it were um, a long time ago. So something, if you're observing something that's like in the Centaurus A picture I showed you, Centaurus is 5 million parsecs away, which is 15 million light years. You're actually seeing it as it was 15 million years ago. You have no idea what it's like now, right? In that sense, you're looking in the past. And in that sense, X-rays are nothing different from normal light. Or if I see a galaxy that is hundreds of megaparsecs away, I'm actually looking at it as if it was that many light years, that many years ago. Right? In that sense, you can see the past. If you're talking about auras around people and X-rays and all that kind of stuff is rubbish. That's not true.
Right, sir. And now a question from Baranya Kumar, and in fact, like I'd have the same question too. Does at some point in time a black hole cease to exist? Like we do know about Hawking radiation, but is there anything more to it? What happens to the singularity when a black hole evaporates?
Very good question. Very good question. What happens to a black hole? Now, you know that black holes can't emit anything, and normally things cease to exist, stars cease to exist by giving up all its energy in some way. How does a black hole give up its energy? The only way we know so far is through Hawking radiation. So yes, if, for example, Hawking radiation can come out of a black hole, then eventually it will give up all its energy in the form of Hawking radiation, and it will cease to exist. That's the only way you can get anything out of a black hole, and that's a quantum effect. Basically, you can't get anything out of a black hole, right? And so you can't destroy a black hole. Once a black hole, always a black hole. Now, if you look at Hawking radiation, very interesting thing is its rate is very small. So, for example, if you have a stellar mass black hole, say the mass of the sun, then if you calculate the amount of time it will take for it to cease to exist by Hawking radiation, the answer is 10 to the power 60 years. Whereas the age of the universe is 10 to the power 10 years. So you see, Hawking radiation is very faint. There's no way you can destroy a black hole in a realistic timescale. If you have a tiny black hole like a primordial black hole, which is, I don't know, 10 to the minus 15 times the mass of the sun or something like that, and you might figure out a way of, in some realistic timescale, destroying it. Right. So black holes are indestructible through Hawking radiation, and we don't know of any other method.
All right, sir. And another question This time from Ankit Kumar. How do we conclude that at the center of the Milky Way galaxy is a supermassive black hole? I mean, you did show us how Sagittarius A was discovered by all the star patterns, but like, can we say the same for other galaxies? Like, is there a black hole at the center of every galaxy and not a star cluster?
Yeah, so this has been done. A lot of energy has gone into doing this in the last 20, 30 years. We now know that above a certain mass threshold, and that's about maybe a tenth of the mass of the Milky Way, the threshold, above which all galaxies, every single galaxy has a supermassive black hole in the middle. And I can talk about how we establish these are black holes. There are many, many, many ways where you can establish them as black holes. I showed how you do it in our galaxy, which is try to measure the size, some limit to the size, and also its mass. And this can be done in other galaxies as well. Now, we also see that under that certain mass threshold, if you go roughly to about 10 to the power 9 times the mass of the sun, 10 to the 8 times the mass of the sun, which is our galaxy is, for example, 10 to the 11 times the mass of the sun. If you go to dwarf galaxies, and there are maybe 30, 40 dwarf galaxies that are satellites of the Milky Way, all of them, none of them have supermassive black holes in the middle, but many of them, ones that are nice and round in shape, elliptical in shape, have what are known as superstar clusters in the middle. So they have, many galaxies have a compact object, a very massive object in the middle, but they turn out to be star clusters. And why do we know they're star clusters? Because you can see them. You can see them in light, and you can measure their mass from light, and you can measure their size, and things like that. So superstar clusters exist in the middle of galaxies, but up to a certain mass threshold, and above that, all of them have a supermassive black hole in the middle. And we also know that the mass of the supermassive black hole actually scales with the mass of the bulge of the galaxy. So you saw Milky Way has a thin disk and a bulge in the middle. Elliptical galaxies have big bulges, no disk. And the mass of the bulge correlates with the mass of the supermassive black hole. And that's why elliptical galaxies have much bigger black holes, much, much more massive black holes in them. Centaurus A, as I said, has 1 billion times the mass of the sun. Our galaxy is a small bulge, and so it has a black hole that's 1 million times the mass of the sun, and things like that. But we haven't found a single big galaxy where there's no black hole in the middle. I hope that answers your question.
Yes, sir. Kalpajit Roy asks, how does a supermassive black hole throw out jets of plasma, as in the case of quasars or blazars?
Good, very nice. So that's actually quite an alive subject for research right now. There are many questions that are associated there, not just how the plasma comes out, but also why they are in very thin jets and not spread around everywhere, stuff like that. It's very alive subject. The reason mass comes out of the center of galaxies and also this you can see in binary systems, in stellar mass black holes as well. You see jets, and that's as following. And I'll give you a very kind of qualitative picture. Mass is coming in. As I said, the mass comes in from nearby systems, or if you are in the center of a galaxy, mass falls in because it's at the bottom of the potential well of the galaxy. A lot of matter falls in the center, and that's the place where it pulls in a lot of matter. Now, black holes cannot take in matter above a certain rate. This is called the Eddington limit. And that is for the following reason. As something is falling into the black hole, it starts radiating, it gets hot, and it starts radiating. And as you know, the radiation from matter at temperature T, it goes as T to the power 4. So the more something becomes hot, the more it radiates. And radiation itself has a pressure. So if something falls in, and as it's falling in, it's radiating. So the thing that's falling in behind it can get stopped by the radiation that's coming out. And so there's a limit that is set by the equilibrium between the rate at which matter is falling into the black hole and the rate at which the radiation is coming out of the matter that's already been falling in, right? And this can be worked out. We do this in normal astronomy class, the Eddington limit. And so if, for example, matter is falling into a black hole from nearby stars or nearby objects at a rate larger than the Eddington limit, it's going to vomit. If I start eating things more than my capacity, I vomit. The difference between my vomit and a black hole's vomit is that I normally vomit after I've eaten something and I throw it up. A black hole can't, vomit something from inside. Once it's gone inside, it's not coming out. The black hole vomits from outside its surface, right? And that vomit is the jet. And that jet is so hot because by the time it's reached the surface of the black hole, it's already become 10 to the 7 degrees hot, as I told you. And at that temperature, everything is plasma because the charged particles are essentially the nucleus and the electrons are separate. It's a charged plasma. And they have kinetic energy so high. I showed you that picture of the jet coming out from the center of Centaurus A, that if you measure the speed of the particles in that jet, they're 99.9% the speed of light. So these are relativistic plasma. They're traveling right across the galaxy, megaparsecs long. And these things are, so jets, so we know the origin of jets, but we don't know very well why jets are so thin and collimated. They're normally, because they're charged particles, they're collimated by the magnetic fields around the black hole. The whole subject of magnetic fields around black holes, also extremely interesting, not well known yet. It's all being worked out now. So this is a very, very alive subject. And with the gravitational waves coming in, this has also become very interesting because we're getting more information from gravitational waves about the black holes. So it's a very, very alive subject right now. Okay. Any more questions?
Yes. Yes, sir, a lot of them. All of this sounds very interesting. So we just had a talk by Dr. Laura on solar flares, and solar flares are jets from the sun. So what is the potential impact that these jets from black holes can cause? Will they obliterate the entire solar system if they pass through, like if Sagittarius A, let's say, ejects something?
Yeah. No. I mean, as I said, these, of course, the scales are very different. The sun's flares, the sun's very near us, the sun's very powerful compared to us. And of course, you can have mega flares. The sun hasn't destroyed us yet, right? We've been together for 4.5 billion years. So people might like to believe that solar flares can be huge, but sometimes they can cause some disruption in our communication system. It's never destroyed us. In fact, we've been monitoring the sun for a long time. So solar flares are fine because that's something that's very nearby. The nearest black hole is 1,600 light years away. So and that's a stellar mass black hole, and the black hole at the center of our galaxy is 8 kiloparsecs away, and it's not alive yet. And so the other thing is that black holes have to be active. They're not active all the time. They're active for about 10 to the power 8 years or so, and then they stop, and then they start again. And that's to do with the supply of gas that goes to the supermassive black holes. This is what quasars are about, and they're active galactic nuclei. Our galaxy is not active. Normally, spiral galaxies, black holes are not very active. They're not very massive. You find a lot of active galaxies in the centers of rich clusters because that's where the gas supply to the black hole is much larger. And so you have elliptical galaxies with 10 to the power 9 solar mass black holes in the middle of these galaxies, in the middle of clusters where the gas supply is large. That's where the action is. That's where the active galactic nucleus is. Ours is a very boring spiral galaxy, a tiny one, and very far away from the sun. So no danger, I'm afraid.
Right, sir. Ayushman Jha asks about white holes, and the death of a black hole has can it become a white hole, and just in general?
No, yeah, a white hole is essentially a theoretical concept, which and you should read the books that I have on the screen right now. Nobody's found a white hole yet. What is a white hole? A white hole is something that is just the opposite of a black hole, which means and everything comes out, nothing goes in. Laws of physics are symmetric, and that's why if there's a black hole, there has maybe a white hole, but I can't see how that will happen.
How plausible is this theory, though, sir?
Yeah, it's allowed in science, but it's not good. So it's wonderful in science fiction to do things like that. And science fiction actually plays around with things that are allowed in science, but not everything that science fiction says is actually possible. And I see many questions coming up to do with time travel, to do with wormholes, to do with white holes. All of that comes in science fiction because they're allowed. But in practice, nobody's worked out how a white hole can exist and form. I told you that even though Einstein's theory, showed that a black hole can form, it took a Chandrasekhar to figure out how a star can turn into a black hole, right? And we now have a theory of how a star can turn into a black hole by collapsing at the end of its life, etc., etc., etc. So you need a scenario that will create a black hole. If you can find one, you become famous and get a Nobel Prize. But nobody's done that yet.
Yes, sir. Deep again asks, could dark matter have some contribution in forming of a black hole?
No, even though dark and black are the same thing, there are two different things here. A black hole is called black because nothing comes out of it. Dark matter is dark because, to some extent, it cannot form stars, and so it cannot start a nuclear reaction that can give you light. Dark matter, as we know it, is in the form of particles. Dark matter is non-interactive. Dark matter is non-baryonic. It's not made up of quarks, not made up of protons and neutrons, made up of some exotic particle. It's there, it's gravitating, but it is neutral. Otherwise, it would have interacted with normal matter and we would have detected it. We haven't detected dark matter except through its gravity. And so dark matters can't form stars. And if it can't form stars, it can't form black holes either. So dark matter has absolutely no role to play in black hole physics. That's the problem. Isn't it practical?
All right, sir. Now we've got a question from Harith. How do the properties of a rotating black hole differ from that of a regular one? And why doesn't spaghettification occur in the case of the former?
Now, I think you're talking about in the Interstellar movie, aren't you? So let's see. Spaghettification happens everywhere. It is not true that it depends on the balance between the spin of a black hole. If the black hole is spinning very, very fast, then it's called a Kerr black hole. Its physics is slightly different from a normal Schwarzschild black hole. The space-time around a Kerr black hole, a spinning black hole, has a certain mathematical formalism. It's not drastically different. The general relativity is the same. It's not violating general relativity, except that there's an extra parameter, and that's the spin. And so the space-time around the spinning black hole, Kerr black hole, looks slightly different from Schwarzschild black hole. But as you go away from a Kerr black hole, space-time goes into normal Schwarzschild black hole, right? So very near a black hole, the actual nature of space-time, the geometry of space-time is slightly different. That's all there is. So nobody's saying that a spinning black hole is completely different from all black holes. In fact, all black holes are spinning to some extent. And some of the black holes that have been found in the LIGO events actually seem to have, so we can measure to some extent, not very well, but to some extent the spin of the black holes that are involved in the gravitational wave events. And some of them seem to have a very high spin. And we know how to put that in to the equations that are used to find the orbits, etc. Yeah, so spaghettification does not happen is not right, but the conditions of spaghettification, which means the tidal force on the matter that's falling into a black hole, slightly different in the case of a spinning black hole, because of course there's an extra source of energy there, which is the centrifugal or centripetal energy that's coming because of the black hole spin. And so the geometry of space-time is slightly different. And so the tidal forces, the balance between the tidal forces and the rotational energy of the black hole will be different than in the case of a static black hole. That's the only thing. It's not true that spaghettification does not happen. It happens under different conditions.
Right, sir. Kalpajit Roy now asks that we know that stellar mass black holes, they appear when a large star dies. Intermediate black holes when like smaller black holes, stellar mass black holes merge. But how exactly are supermassive black holes formed? Do we have a theory for them?
Very good question. Very, very good question. It's not understood yet. In fact, we don't even know how intermediate black holes can come. As I said, till 2 or 3 years ago, it was not even shown that intermediate black holes exist. We know that stars go supernova and compact objects in the middle can form black holes. Stellar mass black holes, we know. Now, we have no idea how supermassive black holes form, because the most massive stars we see in our galaxy are about 100 solar masses. So they would turn into black holes that are less massive than that. There are no stars that are 1,000,000 times the mass of the sun. So you cannot form the supermassive black holes from massive stars. Now, it was proposed in the 1980s that maybe the massive black holes, the stellar mass black holes, merge to form these bigger black holes. But it was pointed out, many things that are pointed out as wrong with this theory. And that is one, then why don't you see the ones that are in between? If things merge hierarchically to form these big things, then you should see 100 solar mass black holes there, which have just merged, and then 1,000 and 10,000 and 100,000. All we don't see any of them. Only now we've started to see 100 solar mass black holes. That doesn't mean that we can go all the way up to million solar masses. So how did they form? We don't know. There are other theories which say that early on in the age of the universe, when the universe itself was very, very small, there were black holes that were very massive. And they formed as primordial black holes. They didn't form from stars, they formed as black holes. And those could have been massive, and those could have been the seeds of galaxies forming around them. Martin Rees is somebody who's written about this. The book that I'm talking about here, some of these books actually go into quite a lot of detail on these theories, and you can look at them. A recent book by Bernard Schutz called Gravity also has a chapter on how such things might form. It's an open question, and it's a very, very interesting question. We don't know the answer to it. But the discovery of 100 solar mass black holes is a step in that direction. It still doesn't give you a million solar mass black holes. Essentially, what they're trying to say is that for 40 solar mass black holes to merge, and these are very rare events, to form million solar mass black holes, you'll need a very long time, and the universe is very young. The universe is only a few billion years old. And in that amount of time, to have 100 mergers, to go from 40 to 80, 80 to 160, 160 to 200, 200, it takes many steps. These are very, very rare events. How can you form so many solar massive black holes in the universe? That's the idea. So somebody has to show a mechanism as to how these things form, and we are nowhere near doing that. Okay, done.
Yes, sir. Very interesting. Ayush Mishra now asks, as a star collapses to form a black hole, can we infer anything about what state of matter the surface of the remnant is in?
There's no surface in a black hole, right? So if a black hole is formed, there's no surface. A black hole has an event horizon, which can't be a surface, because then you actually detect the surface as something that's radiating as a black body, and you don't, right? So the black hole does not have a surface. It just has a distance from the center beyond which you can't see. Black hole doesn't need to have a surface. Actually, the black hole is a singularity right in the middle of that. It's nowhere near the event horizon. So we don't know there's a surface there. If that was the question, I don't know whether I understood the question.
He's asking for the surface of the remnant. This could be the layers of the star that are left behind.
Yeah, so if, for example, the part of the star that's left behind could, before going into the black hole, could become a white dwarf or a neutron star and that kind of stuff. Those remnants, of course, have surfaces, and we've seen them. I mean, for example, when we see pulsars, we see the surface of neutron stars. We can detect white dwarfs in various ways to do with X-rays and ultraviolet, stuff like that. So we see surfaces of these remnants, yes, if that's what he's talking about. But if it becomes compact enough that the surface goes inside the event horizon, then that turns into a black hole and we don't see the surface anymore.
Right, sir. And Prashun's asking can we say a black hole is a state of matter? As like when particles come closer, they become a solid. But if I bring particles very, very close, do they become a black hole?
The state of matter, the state equation of states essentially is telling you that there is a relation between for example, I mean, it's a thermodynamic term, isn't it? State, which you can define it in terms of solid, liquid, gas, and plasma, the four states of matter, and all of them have properties which link their pressure and temperature and density in some way, right? So it's a kind of thermodynamic description, and all that boils down to the forces between the particles. So, for example, a solid is a solid because the forces between the molecules that constitute a solid has a certain, description, and that keeps the solid a solid. And in the transition of going from one phase to another, that interaction between the constituent particles changes, right? And at the other extreme, you have plasma, where you have charged particles that are completely separate from each other, and their interaction is just long-range electromagnetic interaction. So here, I don't see how a black hole's description as a state of matter comes in, right? I mean, it's really not related to this kind of a description. It's completely different. It's to do with its gravitational properties. And so it's best to think of the black hole in terms of a state, if I may use that word, in space-time, in which you think about singularity, and the singularity is covered by an event horizon, so you can't see the singularity, right? And you really can't have, and outside you can only feel its gravitation, and inside you don't know what it is.
Right, sir. Prajakta Mane asks, can we expect gravitational waves from the tidal disruption events?
You can expect gravitational waves in any way. I mean, if you jump up and down where you're sitting now, you are actually emitting gravitational waves because you're disturbing space. Space-time is disturbed by any massive object moving in an asymmetric manner, right? So as long as you keep your motion asymmetric, you're generating gravitational waves. So tidal disruption, of course, generates huge amount of gravitational waves. Question is, how would you detect them? And we've just about detected things that are that come from the merger of the most massive and exotic objects in the universe, and we barely detected them. Yeah, 100 years later, I mean, like Galileo barely detected, some moons around Jupiter with his little telescope. We are at that stage with gravitational waves. I'm sure the technology will get better and better and better, and then we can detect your tidal events. Sure. But anything that's tidal, I mean, tidal means that it's asymmetric, right? Anything that's tidal is related to gravitational waves, absolutely.
Right, sir. Prakhar Khurana now asks, is it possible for us to detect whether the bending of light, including some quantum particles and the wild and carefree bosons, is dependent or the function of radius, or the function of radius of the mass of the black hole?
I think I should wind up. this is, let's see if there are any questions that are related to what I said today. If they're not, then we can wind up today.
All right, so I'll look for questions. I mean, there are a lot of them. Roshan Pathak really wanted to ask.
Last question.
It'll be hard for me to choose someone.
Okay, then
I'll ask like Roshan Pathak's question. When a charged black hole evaporates and ends, doesn't it violate the conservation of charge?
No, it just passes on the charge somewhere else.
That's the answer.
Right. So if something, you know, if the black hole ceases to exist, that charge has to go somewhere else. Charge cannot be destroyed. But that's a very good concern. A black hole can have charge, and if it ceases to exist, and it won't really, but if it ceases to exist, it gives up its charge to something else.
All right, sort of the last question from the question that I just read from Prakhar Khurana. Is it possible for us to detect whether the bending of light is dependent or on the function of radius of the mass of a black hole?
Okay, so I didn't talk about the bending of light, and that's a consequence of this whole thing about space-time being bent. Now, whether they are bosons or quantum particles, everything going along space-time goes along the geometry of space-time, right? It normally follows if the space is curved, it'll follow curved space, and it follows basically Fermat's principle, which means that from point A to point B, it has to go along the optimal path, right? So it doesn't matter whether it's bosons, whether it's particles, they all go. Now, so you are talking about bending of light around a black hole. That's what I understand. But you know, it doesn't need a black hole for bending of light. But anything gravitating can bend light. Light that's passing the sun is being bent. Light that passes a galaxy is being bent because the local space-time is bent. Okay, so now, if I understand your question correctly, you're talking about the bending of light being dependent. Your thing is not framed very well, so I don't understand your intention. But it depends on whether it depends on the mass and the radius of the gravitating object. It doesn't have to be a black hole, as I said. It can be a star. Space-time, the bends, the curvature of space-time certainly depends on the mass of the object that's causing the curvature. And of course, it depends on the radius from it, or the distance from it. So so the farther away it is from the gravitating object, the curvature will be less. And similarly, if the mass is high, the curvature will be more at that same distance. So so you're saying whether there is a degeneracy between the two parameters, which means that can you differentiate between whether it's due to the mass or due to the distance from? This is how I understand your question. And of course you can, because it is to do with how this formula works. There are many ways. I mean, it's essentially a geometrical problem. So you can increase the mass, and thus the bend of the light or whatever particles is going to have a certain curvature, and then the radius. And from one point you can't, but if you look at the whole trajectory, you can essentially model this this entire phenomenon and try and figure out what is due to the mass and what is due to the radius. It's being done all the time. The entire study of gravitational lensing works on this particular principle, and now one does gravitational lensing of gravitational waves. One does gravitational lensing of a stream of particles. Either they are carefree bosons, as you call them, or they are essentially particles. this can work, and this whole subject of gravitational lensing essentially works on this. Okay.
Right, sir. That's where we'll end the question answer round. I'm so sorry for all the people whose questions couldn't be picked up. I know it's a very interesting topic. Dr. Somak, on behalf of everyone here today, on behalf of AstraX, on the behalf of IIT Mandi, big thank you for taking the time to speak to us on the super interesting topic that was just touched today. Your points on calling friendly black holes, although I don't know how the image of a stellar mass black hole eating their lifelong partner and of Centaurus A being too greedy and eating up everything is supposed to help. But thanks a lot for calling it to be basically a star that we can't see, the friendly black hole, and discussing the history, how Schwarzschild solved the equation during the World War One, his unfortunate death, and then the intricacies about studying Sagittarius A or any black hole, adaptive optics, the Keck, detecting stellar mass black holes, the X-ray detection techniques, the Chandra telescope, AstraSat, and all of this was really really informative. The questions that were answered, we're great for that, and we thank you for what you do for others in the community. Once again, on behalf of AstraX, a big thank you to you.
Thank you, and please don't have nightmares. Black holes are really quite. Thanks. Bye.
Right, sir. Thanks a lot, sir.